Okay, so let's do another example. Remember the instructions for this example were find the domain of each function. So our second function here is g of x, which is defined by the rule where the output value is determined by the square root of x squared minus 4x plus 3. Or remember where x is your input value. So whenever you're trying to find the domain of a function like this, and what I mean by that is when the answer is not just immediate, something you can just look at and instantly answer the question, you want to identify what exactly you need to be true. So what needs to be true for this function to be defined? Well, you've got the square root of something. Whenever you've got some expression inside a square root, you need that expression to be greater than or equal to 0. So let's start with that. We need x squared minus 4x plus 3. We need that to be greater than or equal to 0. Okay, so that's the first thing we want to identify. Now, the question becomes, when is this inequality satisfied? For what values of x is this statement true? Okay, and in order to answer that question, it's going to help if we factor the left-hand side. So if this actually factors over here as x minus 3, x minus 1. And if I write that as greater than or equal to 0, I'm really just rewriting the inequality in a different form. But it is the exact same statement. Okay, if you remember how to factor expressions like this, these are called quadratics. If you remember how to factor them, great. If not, don't worry about it. Take my word for it for the moment. And once we finish this example, I'm going to do a little reminder up here on the side of the page. So, but for now, this will factor in this form. So just let's work forward from this now. Okay, let's solve something which I'm the one that I use this terminology. I'm not sure how standard it is, but I call this the associated equation, right? We're trying to solve an inequality up here. Well, if I take this greater than or equal to sign and I replace it with an equal sign, I'm going to get this equation. Now, which of course this equation is not the same thing, but it is something we're still interested in. We want to actually find the solutions to this equation, and we're going to use those solutions to solve this inequality. So let's start down here. How do you solve an equation like this? Well, you've got a product of two factors that is equal to 0. That's going to happen in one of two ways. Either the first factor is equal to 0, x minus 3 is equal to 0, in which case you'd get the solution x equals 3, or what's another way this equation could be satisfied? This factor over here, the x minus 1, that could be equal to 0. That's another way that this equation could be satisfied. So if x minus 1 is equal to 0, that's the same as saying x is equal to positive 1. So those are the two solutions to this associated equation. So these are not, we're not done, right? All we did is find the solutions to this equation, but we want to find all the solutions to this inequality, which there may be many, many more, right? So, but we're going to use these values to do it. So what we're going to do is we're going to draw ourselves a table. I'm going to start like that, and then, well, there's going to be 3 rows. One row is going to be for this first factor, x minus 3, right? We've got this factor, and we need another row for this factor, x minus 1. Okay, so that is how we're going to start. And now we've got an extra space down here. I'm going to write LHS, and that's just an abbreviation for left-hand side. And just to clarify what I mean by left-hand side, I'm talking about the left-hand side of this inequality up here, right? So the left-hand side is actually the product of these two factors, as you can see here, right? The left-hand side is literally the product, okay? So that's how you can set up your rows. Now for columns, we're going to draw a line here and a line here. Now why is that the case? Well, I'm drawing one vertical line for each of the solutions that we had to the associated equation. So I've got one for the number 1 and then one for the number 3, right? Because those were the two solutions to this equation. So if I had another solution, well, I'd have a third line drawn down. And make sure you write them as you go from left to right. The numbers should be ascending or growing. So I start with the smaller numbers on the left and work your way to the right with the numbers gradually going up. Okay, so now we've set up our table. We're going to fill it in, but we're going to need to do something. We're going to need to choose some sample points. So we're going to need to pick a point over here, a point over here, and a point over here. Okay, so for this point, we're going to pick something that's smaller than 1. And you want to pick a nice number if possible, so something easier to work with. How about 0? Whenever I can pick 0, I always choose to do that because it's a nice number to work with. Then here we're going to need something between 1 and 3, so it makes sense to pick 2. Just go with a simple option. And then over here, something greater than 3. I'm just going to choose 4. I like to do whole numbers if possible. You could do 3.14 if you want. You could do pi, you could do 37, you could do 3 million. Any option any number that is greater than 3 is an option to you here. But 4 seems to be the simplest choice. Okay, so what you're going to do now is you're going to take those 3 sample points and you're going to plug them into these factors. And you're going to see well, you're going to see what it's equal to, but really all you care about is whether it's positive or negative. So for example, if I take 0 and plug it into x minus 3, I get 0 minus 3, which is negative 3. Now I don't care about the negative 3, I just care about the negative. So we're going to write a negative in that square. Okay, what about for x minus 1? If I plug 0 into x minus 1, I get 0 minus 1, which is negative. Right? It's negative 1, but you just care that you care about the positive or negative. That's all you care about. So now if I plug in 2 to each of these expressions, I'm going to get a negative for the first one and a positive for the second one, right? Because if I plug in 2 here, I'll get 2 minus 1, which is positive 1. So that's why I had a positive. And if you plug in 4 to each of those expressions, you're going to get a positive for both. And in the last row, when we fill in the last row, now you're going to see why we care about this. Because remember, the left-hand side, that is the product of those two factors. And we know we can determine the sign of the product by looking at the sign of the factors. For example, a negative times a negative gives us a positive. What if I do a negative times a positive? Well, then I'll get a negative. Right? You see what I'm doing? I can fill in the last row just by looking at the signs of the factors. And then finally, a positive times a positive is a positive again. Okay, so actually this table is going to answer everything for us because remember the left-hand side is this expression here, and we wanted to solve this inequality. So we were asking the question, when is this product greater than or equal to 0? Well, it looks down here like it's greater than or equal to 0 over here where it's positive. It's greater than or equal to 0 over here where it's positive. But in here it's negative. So those are not going to be part of the solution to this inequality, or equivalently, the domain of this function. So that's how you can use this table to get your answer. You want this column down here, and you want this column down here. But you don't want to include this column in the middle. So you're not going to include the points between 1 and 3. Okay, so our domain, we can answer the question, the domain of G. It's going to be this column here. So all the numbers that are less than 1. So negative infinity all the way up to 1. And actually, what about the point 1 itself? I'm going to include it with a square bracket. And the reason for that is, remember, we just wanted to know when this product is greater than or equal to 0. And x equals 1 happens to be one of the places where this equation is true. So in other words, when it's equal to 0. So 1 counts as a solution to this inequality. And so does the number 3. So that's going to be our first piece over here. And then we want to union it with this piece over here. So we're going to union it with the interval from 3 to infinity. So that's how you can write down the domain. And just because I really enjoy it, I admit, I'm just going to draw the picture anyway. It doesn't take too long and it's nice to get a picture. So we've got the important points 1 and 3. We're going to include them both. Right, and we're going to shade in this side. And then we're going to shade in this side, just so you have a picture of what that domain looks like. And this is, of course, the real line. So I'm going to label that. Okay, so that's our domain. Now, I promised you that I would go back and I would mention the details behind this factoring. Just for anyone who forgets how to factor quadratics like this, here's the method. Okay, so this just for the factoring. Okay, so if I have x squared minus 4x plus 3, I don't care about the inequality, I just care about this quadratic expression. Well, how do you factor these? Well, remember, as long as you're written in this format where you've got an x squared term, an x term in the middle, and then a constant term on the right, you're going to do the following. You're going to find yourself two numbers that add to the coefficient of the middle term and multiply to the constant term. So you want to find two numbers that add, I'll just jot this down, we want to add to -4, and you want to multiply to +3. Okay, you don't have to jot this down. I'm just writing this down for the purpose of our conversation. Quite often this should be internalized when you're trying to do these problems. So you want to add to -4 and multiply to 3. So pause the video, give yourself a few seconds to think about it. But then once you resume the video, hopefully you got the answer. But the two numbers that work are actually -3 and -1, right? They multiply to +3 and they add to -4. So what you're going to do with that now is you're going to use those two numbers to decompose this middle term. So I'm going to write this is really, you're using the distributive property. I'm going to write this as -3x minus x. right? The -3 and the -1. That's how we use those two numbers to decompose this middle term. And now you're going to factor each of those two terms separately. Let me actually put a bracket under here. You want to factor these two terms and you want to factor those two terms separately. So the first two, if I pull out, well, what can I factor out? I can pull out an x. So I'm going to get x times x minus 3. And then for the second two terms, well, I'm actually going to pull out that negative. Whenever you have a negative in between the two groups of terms, just factor out the negative along with whatever else. But since we can't factor anything else out, all I'm going to do is factor out the negative. So if I pull out a negative from the negative x, I'm just going to get positive x. But if I pull out a negative from the positive 3, I'm going to get negative 3. And now I actually have, I'm going to highlight them again. I have two terms now, which both have a common factor of x minus 3. So if I pull out that x minus 3, well, for the first term, if I pull out the x minus 3, I'll just be left with the x. Right, so I'll have x for the first term, and then over here, if I pull out an x minus 3, well, that's the entire term, so I'm just going to be left with a 1. But since there's that negative there, I'm going to have minus 1 here. Okay, so that's how this factoring happened. So that's just a little bit of a refresher. Every single term, usually right after I do this, somebody in the room will always ask me about the diamond method, and if that's all right, and if that works as well. Yeah, it works. I don't cover it. I don't particularly like it myself. But as long as you do it, my understanding is it will work just fine. But I like to use the distributive property carefully and show all my work rather than using the diamond method. But if you like the diamond method and you're used to using it, that's fine too. So there's no problem with that. Okay, so that's finding the domain. So this was just the factoring step between here and here. But this is really your workflow for solving an inequality like this. Okay. I want to define something new here, and we'll finish the last example on this page. So I wanted to talk about the graph of a function. So this is a new definition. So the graph of a function f is defined by the following. So the notation we use is we just write the word graph, and then we put in brackets the function f. So this is the graph of the function f, and this is defined as follows. And we're going to use set builder notation to write down the definition. So really a graph is a set of points, right? You might think of the graph as a picture because that's usually how you express it, and we'll do that in an example down here. But formally, a graph is just a set of points. And the points all have the following form. They've got two coordinates. So the first coordinate I'll label as x, and I'll label the second coordinate as f of x. So this is a very specific form of a point. The first coordinate can be, well, we'll put a restriction on the first coordinate over here. But the second coordinate specifically has to be the output from the function f when you plug in the first coordinate. Okay, so let me repeat that carefully. The second coordinate is always going to be the output from the function when you plug in the first coordinate. So that's a very specific form of a point in the graph. And the criterion that must be satisfied is just simply, well, this x, it can't just be anything, right? I can't plug in absolutely anything to the function. I have to make sure it's in the domain of the function. So that's why the criteria we're going to insist upon over here is we're going to say that x has to be in the domain of the function f. Okay, so that is actually the formal definition of a graph. And I'm going to be totally honest with you, we're not going to work with that all that much, but I do want to equip you with that in case you haven't seen it in a while, or if you haven't seen it ever, now you've definitely seen the formal definition of a graph. But usually, you graph a function with a picture, right? We do it with the Cartesian plane. So let's do that down here. Sketch the graph of this function. F of x is equal to x squared minus 1. Let's start by drawing ourselves a Cartesian plane. So, for how long it takes to graph something, it really only takes an extra few seconds to just go grab a ruler, get it out, and draw the axes carefully. Right? Everyone wants to avoid that step, but really, how long did that take? Right? I got my y-axis, my x-axis, and a point in the middle, and this is the Cartesian plane. Okay, so that notation, you see it's like the blackboard R that stands for the real numbers, but I put a little squared on it, right? Because I got a copy of the real line here, which I've labeled as the x-axis, and I've got a copy of the real line up here, which I've labeled as the y-axis. So there's two of them, and they intersect right at the origin here. So, and the origin is the point 0, 0. Let me add that in. So 0, 0 is equal to the origin. If you hear that word, just a reminder, that's what that means. Okay, it's the point where the two axes intersect. This is the origin here. Okay, so how do you get your graph now? Well, you're going to choose some x values. Right, so let's draw a table. This is one way to graph this function, right? I just want to remind, why am I choosing a table of values? Because I want to really show how the graph that we get over here really matches up with this definition. But quite often, if you already know how to graph this function, then you can use whatever methods that you're already familiar with. It would be typical to just go right to the graph. We know this is an upward facing parabola shifted down 1 unit. But I just want to run through the table of values thing anyway, just once. Okay, so pick a handful of x values. These are going to be your input values for the first coordinate. And then your output values are going to be, well, they're going to be y values. Because really, you're graphing the relationship. Let me jot it down here. You're graphing the relationship y is equal to f of x. This is hidden here in any graph almost, although you don't typically write it. But that's why y is actually the output value, f of x here. The y coordinate of each point. So we're going to pick some x coordinates. How about if you have some better ideas, go ahead. But I typically just start with those points. If I don't have any better idea or any specific reason to choose other points, these are the ones I pick. 0, and then 1 and -1, and then 2 and -2. That quite often will work fairly well. Okay, so what you're going to do is you're going to take these 5 x values and you're going to plug them into the function now to figure out the corresponding y values. So let's just do that for 1 or 2 of them at least. So if I take f of -2, well, the rule says square the input value and subtract 1. So I'm going to get f of 2 is equal to -2 squared minus 1. -2 squared is 4, so if I subtract 1, I get 3. So that means the y coordinate of this first point is going to be 3. So now you've got yourself a point. Let's do that with the other 4 values. So f of -1, you're going to get -1 squared minus 1. So this is going to be -1 squared is just 1. Subtract 1, you're going to get 0. Okay, so this one is 0. So that's how you work them out. I'm just going to fill in the rest now. You're going to end up getting -1, 0, and 3 for the other 3 values. You can work them out carefully in the exact same way, but that's how you get them. So I won't show the details for that. Okay, so now we're going to need to plot these as points. So this is a point here. There's a point on the graph that has an x-coordinate of -2 and a y-coordinate of 3. So let's do some labeling on our graph. It doesn't have to be perfect, but let's say this is 1, 2, 3, like that, right? That gives a pretty good idea of the scale. And then for the y-axis, I'll go 1, 2, 3, and I don't have to label every single notch. If I were to put, say, a 3 here, it's pretty obvious that I mean for each of those notches to be a single unit, right? So especially since I've been so specific down here. And these aren't going to be perfectly spaced since I'm not strictly measuring them, but do your best. And you can always get away with things being less than perfect if you label them, right? So just to be, how about I put a -3 over here just to be specific, and then now I'll go 1, 2, 3 down in the negative direction. I could put a -3 down here. That's definitely, I'm very safe. I've done lots of labeling. There's no room for confusion. Okay, so first point, -2 and 3. Look for the point -2 on the x-axis and the point 3 on the y-axis. And where do those 2 notches intersect? They're going to be up here, right? We've got ourselves a point right there. What about -1 and 0? So -1 on the x-axis, and then on the y-axis, 0 is right here, right? That's actually at the origin. So we were going to have, that's where y equals 0 is on the y-axis, but since the x-coordinate was -1, we're going to move over here and put a point right here. 0, -1, that's going to be this one right here. You see, I always like to say you're just playing Battleship, right? X equals 1, y equals 0, that's going to be this point here, and then x equals 2, y equals 3 is going to be this point up here. So you get those 5 points, they give you a rough idea of what the graph looks like. If you want a better idea, you can always pick more points. Imagine if I picked 1,000 points here, and then I connected the dots, I'd have a beautifully connected curve. And that's actually what graphing software does. Quite often that's the method they'll use. They'll just plot so many points that the graph ends up looking almost perfect in the end. Okay, so you connect the dots and you get an idea of the behavior of the function just by looking at its graph. Okay. So that's one way. That's called using a table of values. Are there other ways to do this? Absolutely. But this is just a quick reminder on how table of values works.